cut a magnet, the end part which is cut will develop south polarity itself. Magnetic length will definitely decrease, but magnetic strength can also decrease, but the polarities won't change. It won't happen that you have north polarity separately and south polarity kept separately. Then fourth was magnetic induction. Magnetic induction means that few substances are there that have the tendency to be magnetized. So these substances which have the tendency to get magnetized, they are temporarily magnetized using the bar magnet. So bar magnet transfers a little bit of magnetic properties to these substances. Best example is take an iron, piece of iron. Take this piece of iron, you rub it with a bar magnet, you put it under the magnetic field and it will be influenced. So these substances that can induce magnetism, this property is called as magnetic induction. We did certain terms related to magnets. First was the magnetic polarity, that south and north exist. Second was the magnetic axis, that the separation between the north and the south pole. And third was the magnetic equator, that was the perpendicular line to the axis. Fourth was the magnetic length. Now we were comparing the electrostatics and magnetostatics, and I asked you to remember the formula of axial and equatorial and all the things that you have done. Yes, Basmi, tell me, what is the electric field due to axial line?
KP by R cube.
Approximated one.
Ma'am, 2 KP by R cube.
How much?
2 KP by R cube.
2 kp by r cube, yes. Fine, 2 kp by r cube. This is the electric field due to the axial line. Now see here also you have the direction when we write. It is same as that of the magnetic, sorry, not magnetic, the dipole. Same as that of the dipole moment. Now here in magnetic field, B along axial will be exactly the same. This will be 2, K will be there. Instead of P, you will have M by R cube. The one more difference will be there. Here your K is 4 pi epsilon. This will be 2P by 4 pi epsilon naught R cube. While this will be 2 mu naught M by 4 pi R cube. Same thing when we are talking about the direction. Same as that of magnetic moment. Got it?
Yes, ma'am.
Now tell me for equatorial point.
KP by R cube.
Just Kp by R cube.
Yeah.
Minus.
Oh.
Minus Kp by R cube. This can be written as minus P by 4 pi epsilon naught R cube. Right? And when we are talking
Yes,
about the direction, this is opposite. Opposite to that of dipole moment. Now coming to magnetic field at the equatorial point, this will be minus Km by R cube. That means minus mu naught M divided by 4 pi R cube. You just need to replace the terms K with this, M with this. And same thing, direction will be opposite to that of magnetic dipole moment. Then the formula of torque. Tell me.
This P cross E.
What?
P cross E. P
Cross E. Torque is P cross E. Or we can say torque is equal to PE Sine.
Sine theta.
Here we can say for the torque, same thing. In case of magnetism, torque is, we did this also. It is M cross B. And this can be written as MB sine theta. Clear?
Yes, ma'am.
Coming to work done. Formula of work done, tell me.
What's that?
What?
Ma'am, I don't remember what's that. Is it the same as potential energy P cos theta?
Yes. Right. This is P dot E. If you remember, minus P dot E. That was the formula of work done, same as potential energy. That was minus PE cos theta. Or for the expanded one, you have minus PE cos theta 2 minus cos theta 1 when it is rotating like this. Here also the work done or potential energy will be minus M dot B, which is equal to minus MB cos theta. This is equal to minus MB cos theta 2 minus cos theta. Got this formula?
Yes, ma'am.
Remember the left hand side one, right hand side you will be able to remember. And I hope you have made it in the tabular form yesterday.
Yes, ma'am.
Please continue from here.
Ma'am, can you scroll down? Ma'am, I'm done. Ma'am, I'm done. Ma'am, I'm done.
Okay. Let's practice one question. Two bar magnets are kept perpendicular to each other, and at a point P, we have to calculate the net magnetic field. So, tell me, Basmi, for let's say this is the first magnet, this is the second magnet. So, the first magnet is the point lying axial or equatorial.
Axial.
What?
Axial, ma'am.
Axial, yes. This is lying axial. See, yesterday we have studied, remember? The axis of a magnet is this. So it is lying on its axis. And for the second one, is it axial or equatorial?
Equatorial.
Equatorial. Because if I take this axis, this is lying exactly perpendicular to it. So here, see, from north to south, if you have the direction, here you will have the same direction for the axial. Okay, and for this one we take it opposite, so south to north like this. This will be V1, this will be V2. Now value of B1 is axial, so it will be 2 mu naught m by 4 pi r cube, right? And this is
Yes, ma'am.
minus I cap towards negative. B2 will be, I'm not writing minus because that direction it will come automatically. This is mu naught p by 4 pi r cube. This is j cap. Now see, here both of vectors are making an angle of 90 degrees. So the net magnetic field will be given by under root of B1 square plus B2 square. So this is equal to 2 mu naught m by 4 pi r cube whole square plus this is mu naught. Oh, I've written p here. Mu naught, this is m by 4 pi r cube. This is square, this is the whole, this much Tesla is the final magnitude. This you calculate and see what is the answer coming. Did you get this question?
Yes, ma'am.
Yes. Write it. We'll see one more.
Yes. Can you scroll down? Ma'am, I'm done.
All right, Basmi, let's see one more question. See, this says show that this is an important question. Okay, mark this important when you write. Show that
Okay, ma'am.
motion of a bar magnet in uniform magnetic field is in SH. And these kinds of questions often come relate. This basically says that see if a bar magnet is kept, so because of torque is existing, we have studied that torque will be there. This torque will allow the bar magnet to rotate in the magnetic field. Okay, this will allow it to rotate in the magnetic field. Here it must create some angle. Here this must move it. This is what will happen. Right. Now we know torque is what? Torque is nothing but M cross B. Torque is equal to MB sine theta. Now a quick revision of what you should know is for linear motions, the force should be equal to minus K of X. We've done this in electrostatics also. There was a question in the first chapter, if you remember. F is equal to minus Kx. This is F is equal to minus Kx. Okay. And the same thing if it is this is rotational. If this is rotational, so torque will be equal to minus K theta. If any of these conditions are fulfilled, we say the body is in SHM. Okay. So we can say we finally have torque is equal to MB sine theta. Now look, these angles that are covered by the body here, these angles are quite less. The angles that how much will a bar magnet rotate? It won't just swing and all, right? Bar magnet will just get deflected because of torque slight. So we can use small angle approximation. Small angle approximation, I'm repeating, when your theta is less than or equal to maximum 15 degrees and not more than that. Okay, we say this is the condition for the small angle approximation. So in this condition, our sine theta is almost equal to, which is tan theta, both of them are equal to theta. Like tan, whatever is the value of sine 7 degree is almost equal to 7. If you have tan 3, so it is almost equal to 3 something. So you can write this as it is as 3 or whatever is the number. So here I can say when I have the value, torque is equal to MB sine theta can be written as MB theta. This is if you write it along this equation, torque is equal to K theta. Can we say from this side K is equal to MB?
Yes, ma'am.
If I write it like this, we can say MB is equal to K. We have got our K. So this shows that this is following. We can say hence it executes SSM. Got it? We did the same thing we have done. We've done already.
Yes,
We
ma'am.
got E sine theta using. Revise that. We've done that. Now K is MB. Now formula for the angular frequency. This is the angular frequency. Angular frequency is omega is under root K by I, so that becomes MB by I. From here, you can write down the frequency. Look, omega is equal to 2 pi nu. The frequency is 1 over 2 pi under root MB divided by I. That's why I marked this question important. This is not just a question which you have to use as a question of magnetics. This can come as a derivation also. And the time period is just reciprocal of frequency. So that becomes under root 2 pi I by MB. Am I clear?
Yes, ma'am.
This is the linear frequency. This is the time period. Okay, Basmi?
Yes, ma'am.
Please write. And write it somewhere that this you have to use this as a derivation, not just a question.
Okay, ma'am. Ma'am, can you scroll down? Ma'am, can you scroll down? Yeah, I'm done.
Okay. Just can you try this question? Then let's discuss it.
Yes, sir.
Okay. Okay. Let's discuss this. Now stop writing with me. Okay. This says that a magnetized needle of magnetic moment is given as 4.8 into 10 to the power minus 2 joules per Tesla is placed at 30 degree. Just give me a minute, Basmi.
Ma'am.
Yes, yes. See, magnetic moment is 4.8 into 10 to the power minus 2 joules per Tesla. This is placed at 30 degrees in the direction of uniform magnetic field. Okay, means you have a bar magnet.
Okay.
Yeah,
No,
you
ma'am, I
said,
just said okay.
okay. So see, 30 degree with the direction of uniform magnetic field. So let's say the magnetic field is like this. This is our magnetic field. And we have a bar magnet. Okay, so this bar magnet is placed at 30 degree with the magnet. Okay. Now see, yes, this says that magnitude of magnetic field is also given. B is given 3 into 10 to the power minus 2 Tesla. This is for Tesla. In fact, this will be magnetic field, magnetic moment is current into area. It says what is the torque acting on the needle. What will be the torque acting on the needle? So torque formula is M cross B
Yes, ma'am.
equal to MB sine theta. This will be equal to 4.8 into 10 to the power minus 2 into 3 into 10 to the power minus 2 into sine 30 degree, that is half. So this will become 2.4. 2.4 into 3 into 10 to the power minus 4. This is 7.2 into 10 to the power minus 4 Newton meter. Okay.
Okay, ma'am.
Please write it. Then now let's see the properties of magnetic field. The way we discussed electric field once, that question often comes. That's a very important part. You write, then I'll discuss.
Okay, ma'am. I'm done, ma'am.
See, am I audible?
Ma'am.
Okay. So now let's talk about the magnetic field lines. Okay. We talked about the bar magnet. So now let's talk about the magnetic field lines. Okay. What exactly are magnetic field lines? These are imaginary lines. Like electric field lines were not actual lines. So these are also imaginary drawn lines, or lines drawn, in fact. Imaginary. These were imaginary lines drawn. Okay. Now, similarly, these are also imaginary lines drawn in the region of the space time. Okay, which we say. So, imaginary lines drawn along the free north. Okay, this is along the free side of the north. when we're talking. Like if you remember electric field, that time I talked and I said that electric field lines are actually not existing. But electric field lines are drawn so that we can see the electric field. That yes, where are the electric field? Right? So see
Yes,
these
ma'am.
imaginary line drawn in the region of space free or free space, in the region of space time. Now, what does this space time mean? This means that around the magnet. The space time means around the magnet, basically in the region of the magnetic field. Okay, along with a free magnet, in fact, a free north pole. I will say a free north pole would move. Good. These are just imaginary lines drawn, and they can be in any shape. They usually form a closed loop like this, like this. They can be like this. Okay. These are all the imaginary field lines. Now we will be specifically talking about the field lines due to a bar magnet that comes in the exam. Okay. So for a bar
Okay,
magnet,
ma'am.
first property, magnetic field lines form closed loops. This is unlike the one which we studied in the electrostatics. That time the closed loops weren't formed. So first point is that magnetic field lines form closed loops. Okay. This means that in case of the electric charges, when plus Q is there and you have minus Q present. So we used to say electric field lines are going like this, electric field lines are going like this. The field lines just move away for these charges. And for the negative one, they move towards. Remember, we have drawn such things in
Yes,
electrostatics. This could never be completed. Look, both the lines are going like this towards it and terminating. From here, this is originating, and from here, it is terminating. Okay, from here, it is originating and terminating. Means there are no closed loops here. In case of a bar magnet, if I draw a bar magnet, like this, you will have the bar magnet present. This is, let's say, the north pole here. Over this side, you have the north polarity. Here, you have the south polarity. In case of a bar magnet, here the field lines, they come out from the north, they terminate towards south, and then within the magnet, they move from south to north like this. Again, from this side to here, to here, to here, back to here, like this. So they are here forming closed loops like this, the field lines. Okay. So remember, what's the direction then
ma'am.
for this? From north to south, it is outside the magnet, and south to north, they move within the magnet inside. It's not fixed. In case of electric field, it was so rigid and fixed. Remember, in case of electric field,
Yes, ma'am.
we like this one in electric field. That's why I've drawn this so that when you draw, you will have it in your mind. Okay. And again, the second point is very easy. That the tangent to magnetic field lines to any point, actually, to any point on the field lines give rise to tangent to any point on field lines give rise to magnetic field. Like in electric field, we had the same thing, magnetic. In case of electric field, the line went like this, and we used to take out a perpendicular here, like this. This would be giving us the direction of electric field. Similarly, here also, if this is one of the lines, you pick any point, you drop a tangent on this point. This will give you the magnetic field, while this one is the magnetic field line. Did you get this point?
Yes, ma'am.
All right. One more point which we discussed there. Closer the lines, stronger or weaker in electric field?
Closer the lines, it will be stronger. For active field, when lines, it will be stronger.
Means when they are denser, here also magnetic field will be strong. Okay, and same thing when it is away, then it will be weaker. Like if I have, let's say there are various magnetic field lines. This is region 1, this is region. So I'll say magnetic field in region 1 is stronger than magnetic field in region. Okay. Could
Yes, ma'am.
or write it till here, then we'll discuss. Till here, is it clear everything?
Yes, ma'am.
Please write it.
Ma'am, I'm done. I'm done. I'm done. Done, ma'am.
Okay, one more thing. There was a concept that two electric field lines cannot intersect with each other. What was the reason for that? Yes, what was the reason?
Ma'am,
Hmm?
gosh, no. There was some reason they couldn't intersect.
Remember, electric field lines do not intersect with each other. There was a concept.
Yes, ma'am.
Yes, so what was the reason?
I don't remember. I think it was because
The reason was that
uh,
if, let's say, two magnetic field lines are there, they are intersecting. So at this point, the direction of the first magnetic field will be this. Direction due to the second one will be this. At the same point, it is giving two different directions of possible, which will be physically impossible. This says that same point, two tangents, right? And if it is two tangents, this means two different direction of magnetic. Why is the first chapter income today?
ma'am, I did go through it.
Hmm?
God, this is- Ma'am, I did go through it.
You did revise. What are you saying?
Yes, ma'am. Yes, ma'am, I revised through it. I didn't go through the theory though, only the formulas though.
Okay. This is the North Pole, this is the South Pole now. When we are calculating the pole strength, remember whatever is the number of field lines. is one. It is whatever is it. Remember the concept that the number of magnetic field line and the pole strength are directly proportional to each other. Number of field lines are directly proportional to the pole strength. Okay.
Okay.
Sixth property. See, if you have a uniform electric field, uniform magnetic field, how did we represent the uniform electric field?
Um, yeah, I think yes, ma'am.
What?
The straight
Yes,
lines, right?
with a
The straight line, right?
straight line. That is right. Some more things, just straight. What about the next one? How should I draw the next one then?
Um,
If I draw it like this, will it be okay?
no, no, I think they're curves. They're not straight lines. They're curves. My electric field are curves.
So electric
Yeah.
field lines can never be straight lines. So whatever we have studied throughout the first four chapters was wrong. I
No,
often
ma'am.
used to write the electric field like this.
No, ma'am. They're not wrong.
They are not curved. Then
They are curves, but
it's not about curve or what. See, first, when you're talking about uniform electric field is always parallel straight lines which are equidistant. We did this multiple times. Okay, so same thing is for this also. Look, they will also be parallel, straight, and equidistant. Okay, to each other. Like
ma'am.
so, these properties differ like this one. So, what are the points here? They are straight, parallel, and equidistant. Okay, you can say if I have three magnetic fields here, V1, V2, V3, V4. I can say B1 is equal to B2 is equal to B3 is equal to B4. That is the main magnetic field B. Is that clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Try to study this chapter with your first chapter. Then you'll be able to understand it better. You'll be able to remember both of these. Okay.
Okay, ma'am.
Please write it.
Ma'am, can you scroll down? Um, I'm done, ma'am.
See, now there's a topic that are certain terms related to magnetism. See, much isn't left in this. What all topics are left, I'll tell you. There's a topic about intensity of magnetization, intensity, and very confusing terms are there. So for that, you need to understand that topic is left, earth magnetism is left, and different types of matters are left. Okay. So it's a very short, small
Ma'am.
chapter. Now, see, cause you understand, then only you'll be able to understand the different concepts, okay, about intensity of magnetization. You have susceptibility, lots of things are there. And when that is finally done, we'll move on to the substances. And in the last, I'll do the earth magnetism. See, first, when you have matter, we know that all of these matters, they are made up of atoms. Yes, matter is made up of atoms. Is that clear? And when we talk about it at a micro level, we can say that there is a nucleus, positive nucleus present, and around it exists the electron that travels. And when this electron moves, see, this is about, see, we are talking about magnetism in matter. Previous chapter was moving charges and magnetism. This chapter is magnetism and matter. We are talking everything about the matter level, means at the atomic level. So this is known as the orbital motion of electron. Orbital motion of the electron. Okay, this is what it is known as. Orbital motion of the electron. Now, when this orbital motion of the electron is there, it contributes to current. To electric current. Now see, now this current behaves like a magnetic dipole. Why? See, this is like a loop. Now this will be producing current. at the very atomic level. Nucleus is there, electrons are revolving around it. So this is in the orbital motion. Now this is contributing to current because electrons have started their movement. So this loop behaves as a magnetic dipole. Now this current loop acts as a magnetic dipole. Because you have numericals from this part. A question is there exactly based on this. Magnetic dipole. So it's like you have a charge which has other things moving, right? And here, if this is the axis, electrons are moving, it is producing current. So simply we can say magnetic moment. What's the formula of magnetic moment?
IA.
IA. Exactly. So this will be I into. Clear?
Yes, ma'am.
Okay. Now, why do we have this magnetic moment? We're talking about this magnetic moment. There are reasons for it. I'll tell you the reasons. Once it came in the board exam also. Look, magnetic moment of an atom is due to first, the most important reason is this orbital motion of electron that we have studied. That electrons move, it leads to current. Current makes the loop act as a magnetic dipole. So see, when a moving current is there across a loop, that is what is the magnetic moment. This is what we studied. Remember, we did a question on based on a square and a circle. So first reason is
Yes, ma'am.
orbital motion of electrons. This is very important because this is the major factor. Okay. Now we did the, remember when I told you the sources of magnetic field, I told you that the angular spin of electrons.
Yes, ma'am.
So angular spin of electrons, this is the next reason. Now, apart these were related to electrons. These were the reasons contributed by the electrons. Next reason is contributed by the nucleus. That the magnetic moment of the nucleus, because nucleus also has charges, right? So there
Yes,
is
ma'am.
a nucleus has an area as well. So this is due to magnetic moment of the nucleus. Why? Reason is that the see in this one we don't consider it much. The reason is that it's very small. Okay, this is very small. The magnetic moment here is very small for the nucleus. And see, this is all related to your quantum mechanics that we'll study. That this all these things we'll study in the quantum mechanics. You have a chapter
Oh,
3I. There we'll study what happens to these electrons and everything. So you don't have to go into the details of it. Neither for this nor for this. Okay, just remember the basics
okay,
of the reasons. Okay, and remember one thing: when we have the magnetic moment of an atom, the point I'll tell you. If I have an atom and I am saying its magnetic moment is m, so this magnetic moment is net magnetic moment due to all the electrons that are present. When we say magnetic moment, that it doesn't mean you're talking about a single electron. It means all the electrons are there, all the electrons have contributed, and finally the net magnetic moment you're answering. So this is the net magnetic moment. Okay, so net magnetic moment is to all the electrons, not just because of one single electron. Okay,
okay, ma'am.
all right, write it till here.
Ma'am, can you scroll down?
What, Basmi?
Nothing, ma'am. Ma'am,